Alright, this is our second lesson of Unit 5. Today we'll be talking about a couple of theorems relating to polynomials. So I wanted you to look at these two questions. They're on the top of your notes. Find the quotient and the remainder when f of x is divided by x minus 5. And then the second part is to evaluate f of 5. So if we want to divide that function by x minus 5, we can use synthetic division with the root 5. Our coefficients are 2, -13, -7, and 4. Hopefully you remember your synthetic division. We drop down that first one, we multiply by 5 and put it in the second column. Add that column up. Now we multiply by 5, put it in the next column. Add that column up. Multiply by 5. Put it in the next column, add that column up. So our answer to our division problem would be 2x to the second power, our original polynomial was power 3, minus 3x minus 22, and we have a remainder of -106. Alright, so the second part is evaluate f of 5. Let's put 5 into the function. So we get 2 times 5 to the third power minus 13 times 5 squared minus 7 times 5 plus 4. So when we evaluate that, and we use our calculator to evaluate that, we get -106. That's weird. The remainder is the same as the answer that we got when we substituted the root 5 into the equation. Huh. I wonder if it's always like that. So in class, we tried it out. And we found that when we divided, the remainder that we got was exactly the same as if we had substituted that 0 into the function. And it worked no matter which 0 and factor we used. If we substituted it into the equation, the answer we got would be the same as the remainder if we divided by that factor. And there's really nothing intuitive about that. It's not something you would just guess would happen. But it is true that it's always the same, and there's a theorem that tells us that that's true. And if you wanted to prove this theorem, you could. It would take a lot of math skills, but the theorem says that if a polynomial is divided by a linear factor like x minus a, if we divide by a little factor like this, then the remainder is going to be exactly the same as if we had substituted that 0 into the function. So it's called the remainder theorem. So let's try to use the remainder theorem to answer this question. What is the remainder when f of x is divided by x minus 1? Well, we could go ahead and divide it, but if we didn't want to divide it, we could use the remainder theorem. And the thing we want to divide by is x minus 1, so we would use the 0, 1. F of 1 is 1 to the third minus 3 times 1 squared plus 8 times 1 minus 4. And if we calculate that, we find that f of 1 is 2. 2 is the remainder. Let's divide it and see if it's true. So we would use the root 1. So we have 1, -3, 8, and -4. So if we actually went through and divided it, sure enough, we get a remainder of 2. So the remainder theorem is just telling us that if we choose to, instead of going ahead and dividing it like I did at the bottom, we can just plug it in like we did here, and we will be able to calculate the remainder using substitution. So here's one that you could practice. If you want to pause the video and see if you can get the correct answer, or you can just keep following along with me. We're dividing by x plus 4, so we can substitute into the equation -4 to find out what the remainder would be. And it's not always necessary for you to write that out if you just want to put it into your calculator and just think about it, but I wrote it out. So if we, let's see, sorry, I'm just putting it in the calculator. If we substitute -4 in for x, we get 1277. It's a huge number. That is the remainder. So if we divided 3x to the 4th minus 7x squared plus 2x squared minus 5x plus 9 by x plus 4, we would get 1277 as the remainder. So here's a good example of a problem where we have to use the remainder theorem to help us answer it. If the polynomial f of x is divided by x minus 2, the remainder is 45. Can you figure out what the coefficient of x squared is? How many x squareds do we have? So if we were wanting to solve this problem and figure out what k is, the remainder theorem might help us, because we would remember that if we substitute 2 into the equation, we should get an answer that is equal to the remainder 45. If we put 2 into the function, the answer should be the same as the remainder, 45. So let's go ahead and put 2 into the function. 2 times 2 to the 3rd plus k times 2 squared plus 4 times 2 minus 15. We know because of the remainder theorem that we should get that equal to 45. So let's simplify some of these terms a little bit. 2 times 2, oh whoops, sorry, that is supposed to be a 3rd power. That's my little typo of the day. 2 times 2 to the 3rd power is 16. 2 squared times k is 4k. Please note the k is not squared. Only the 2 is squared. 2 squared is 4. That 4 is multiplied by the k, so that's a 4k. This 4 times 2 is an 8, and minus 15 is equal to 45. Well, you could combine the like terms, or if you want, you could just start moving things over. -16 to both sides, -8 to both sides, 15 to both sides, and we end up with just a 4k equal to, and if we add that up, 45 minus 16 minus 8 plus 15, and you evaluate in your calculator or in your head, you should get 36. So if we do that last step of dividing by 4, we figure out that the k value, the coefficient of x squared, must be 9. When f of x is -7x to the 3rd minus 4x squared plus mx minus 10 is divided by x plus 4, the remainder is 6. What is the value of m? So this is just a practice problem for you to try. If you want to pause the video and try it, that would be good. So we're dividing by x plus 4, so we can use the root -4 in the function. And if we do substitute -4 into the function, the remainder theorem tells me that that will be equal to the remainder, which is 6. So let's go ahead and substitute that in. And again, it's equal to 6. So negative 7 times negative 4 to the third power is 448. Negative 4 times negative 4 squared is negative 64. This term right here, it's an m times a negative 4. So it's a negative 4m minus 10 equals 6. We're going to try to get that m by itself. So I'm going to subtract that 448. I'm going to add a 64. I'm going to add 10. And I get negative 4m is the only thing left on that side of the equation. And over here we get negative 368. So when we divide by negative 4, we find that m is equal to 92. So that missing coefficient in our original equation should have been a 92. But why on earth then would we be interested in these remainders? Why is it useful to be able to calculate a remainder quickly? Or is there maybe a particular remainder that we are most interested in finding? Well, it turns out there is a remainder that is the most interesting to us. Most remainders are not that interesting, but if we have a remainder of 0, that means something. So let's think about what it means for a minute. If I have 36 and I divide by 4, I get the answer 9, and it has 0 remainder. If I had a 72 and I divide it by 9, I get 8 with a remainder of 0. What does it mean to have a remainder of 0? Well, for numbers, it means that that number you divided by, that divisor, it means that is one of the factors of the number. This means that 4 is a factor of 36. This means if I divide by 9 and I get 0 remainder, that means 9 is a factor of 72. Well, it works the same way with polynomials. If we divide and we get a remainder of 0, we have found one of the factors. And that's called the factor theorem. So the factor theorem says if you have a polynomial and it has a factor of x minus k, it has to be the case that f of k is 0, which is the same as saying it has a remainder of 0. So in other words, if we know the function is equal to 0 for a certain value, it means that that associated factor is one of the factors of the function. Or if we know one of the factors, then we know it's going to have a remainder of 0. So let's see if how that will apply. So here's a polynomial f of x. It's a quartic polynomial. I want to know, is x plus 2 one of the factors of this polynomial? Well, it's a quartic polynomial, so potentially it could have 4 factors. I just want to know, is x plus 2 one of those factors? Well, I could use the 0, negative 2 to test that. And if we substitute negative 2 into the equation, and I'm not going to write that out, you should just substitute it in your calculator. It's not really necessary to write out that whole long thing, but in my calculator I'm doing negative 2 to the 4th power, and I'm adding 2 times negative 2 to the 3rd power, and I'm subtracting 7 times negative 2 squared, and I'm subtracting 8 times negative 2, and I'm adding 12, and if you do all that, you get 0. Well, that 0 means there is no remainder, which means that, yes, x plus 2 is a factor of f of x. Let's test another factor. What about x minus 4? Well, if we wanted to test x minus 4, we would use the 0, 4. So we would plug 4 into our function, and if we do that, it's a little bit of calculator work here. And we can evaluate it. And we get 252. And this remainder here means that x minus 4, the factor we were testing, is not, it is absolutely not a factor of the function f of x. So just by figuring out if the remainder is 0 or not, we can tell if it is a factor of the function. I'm going to skip this for the video. You could test those two factors if you wanted. Here you would be using -3 to test the factor x plus 3, and you should find that, actually I don't even remember off the top of my head. I don't remember. And on the other case, if you want to test that, you should be using 3. Okay, so here we go. One of the factors of x to the third plus kx squared plus 23x minus 35 is x plus 5. Can you figure out what this coefficient has to be? What's the value of k? Well, we know that this is a factor of the polynomial. So what that means is if it was divided by that x plus 5, we should get a remainder of 0. Okay, so in our equation, we're going to substitute -5 into our equation. And when we do that, the answer we should get should be equal to the remainder, which is 0, because x plus 5 is a factor. So let's simplify and clean this up a little bit. -5 to the third is -125. This term is 25k. The k is not being squared, only the -5 is being squared. 23 times -5 is -115. And we, again, know that's equal to 0. So we're trying to work towards getting that k by itself. Add the 125, add the 115, add the 35, and we end up with 25k is equal to 125, 115, and 35 altogether is 275. So if we divide by 25, we find that k is equal to 11. So in class I had them do this activity. Polynomial f of x is given there. We tested each of the factors to see if we could try to find which one of those were factors of the polynomial. It might be a good activity for you to try. That's it for the lesson. It's kind of a short lesson. Hopefully you have a good understanding of it. If you need help with this, please come in and I'll give you some help. And but it would be a good idea if you can learn this concept at least a little bit before our next class period, because we will be using it pretty extensively in class. So that's it for lesson 2. We're halfway through our unit now.